Okay, this video is on the change in concentration with time notes. It's a packet that looks like this, and we're going to be talking about first order, second order, even zero order reactions, and how we can graphically interpret some pieces of information. So this is a little bit of a different kind of discussion. There's a little bit of background information, but most of the background in this actually lies in calculus, and so we very much steer clear of the background information for this section. Okay, so the first thing, I probably should have put this like before your heading of first order reactions. This is kind of like a takeaway point, and it's like the intro to this section, and it just says that rate laws, so now we know how to write a rate law, we know how to determine orders, all that good stuff. But rate laws can be converted into equations that can tell us the concentration of a reactant at any time, and that can be very helpful. In certain instances, you could think maybe medically why that would be helpful to determine the concentration of a medicine, perhaps in your body, determine the concentration of a poison, okay, how much poison is left after a given amount of time. And these equations can be graphed, and it's the graphical interpretation of these equations that's very important to us. And so this is just kind of a takeaway point, okay, that we can take these rate laws, we can turn them into a graphical representation, and then we can analyze a couple things from the graph. And it's actually kind of neat what all we can determine from the graph of a rate law. Now, as I said before, this lesson or this section is highly rooted in calculus, okay? And obviously this is not a calculus-based class. So we're going to skip over quite a bit of how they figured this out, and you're just going to assume that what I'm telling you is correct. and I am. I'm telling you correct information, but there's not a whole lot of why background to this, okay? Because it is rooted in calculus, and I am most definitely not a calculus teacher. So, okay, so that was kind of like a takeaway point, so to speak. And now we're going to talk about first order reactions, okay? So obviously a first order reaction is something where the rate depends on the concentration of a single reactant raised to the first power. Okay. So, it could be something like this. Right? Would be my rate law. And maybe my reaction is A going to make products. Okay. Remember, we can't really tell that this is first order from this equation, but we're just assuming that I have been told it's first order. Okay. So this whole first section talks about a first order reaction. So again, we're jumping way into some calculus, and there's something that's called an integrated rate law. So it's still rate law, okay, but calculus has been done to it. It's called an integrated rate law. And that equation, it looks like this. So just give me a second to write it, and don't panic. Okay, so this is what we call the integrated first rate law, okay? And I'm sure you know what these symbols are, but we'll do a quick discussion and I will label them for you. Okay, so this is the integrated first rate law. In no way would this need to be memorized. It's given to you on the AP Chem cheat sheet, so to speak, okay? So it's just given. It's just like PV and RT is given. Okay, so, Ln, of course, is the natural log, right, which is just a mathematical function. And so this equation says the natural log of the concentration of A, right, we know what this means, brackets mean concentration. So the natural log of the concentration of A, which is, of course, my reactant, at some time t, okay? That's what T, it's a little lowercase t, not capital T, which is temperature, right? So this is not temperature. So this is the natural log of the concentration of A at some time T minus the natural log of the concentration of A. Now this is like a 0, okay, or it's called like a naught is the symbol. And this means a time of 0. So this is the initial concentration. Okay, so the natural log of the concentration of A at some time T minus the natural log of the initial concentration of A is equal to negative K, that's the rate constant, times T, time. Okay, again, it's lowercase t, not capital T. So you might be asking, like, what the heck would I even use this for? Okay, well, we could use it for several things. It's just like any other equation. I have 4 pieces of information: the concentration at time t, the initial concentration, the rate constant, and time. So if I knew any 3 of these missing, or 3 of these pieces, I could always find the 4th. So let's say you knew the concentration, of a reactant after 4 minutes, right? And you knew its initial concentration, and you knew that time between them was 4 minutes, you could find the rate constant with just a little bit of algebra. Okay, or if you knew the rate constant and the time and the initial concentration, you could figure out how much of something is left, okay? And so that's where we had referenced before. It could be very important with maybe medical things or poisonous things, checking to see how much poison was left in something, or a toxin or something like that, okay? So I know still right now you're kind of like, ugh, I don't really, see the see the point here. But it's coming. So let me get rid of this so I don't run out of space. And now we're going to talk about graphically what I can do to this. I'm going to rewrite this. Okay, now hear me out. I will explain to you why I'm going to do this. I'm going to solve this equation for the natural log of the concentration of A at time t. All right, so I want this by itself, which means I'm going to take this piece over to the other side. So I'm just going to add it. And all of a sudden, I would get an equation that looks like this, okay? All I've done is algebraically rearranged it. I just took this term to the other side of the equation. That's all I did. Now, we're going to talk about graphically what this would look like, okay? And you might be like, how in the world would I graph this? Well, what's kind of neat about this is, I was looking for another color marker, but I can't find, oh, there's one. What's kind of neat about this is this equation, you might not see it right now, this equation is actually written in slope-intercept form. This is y, this is m, x, and this is b. So what does this mean? Well, so what this means is if I graphed the natural log of A at some time t on my y-axis versus time on my x-axis, I would get a line that has a negative slope. Okay, see, m here is negative k, so the slope would be negative. And so if I graph this, I would get something that looks like this. And I guess I should continue this, because where this line crosses the y-axis, this would be the natural log of the concentration of A initially. See, look, it kind of makes sense. Like, initial concentration is high, and as time goes on, the concentration is decreasing, right? Remember, A is a reactant, so of course it's going to get smaller. So you still might be like, what the heck? How does this apply to anything? And this is how it applies to anything. Well, hold on, one more thing. So the y-intercept here is the natural log of the initial concentration, and the slope is equal to negative k, which is the rate constant. So here's the kicker. Here's the big takeaway. If you graph this, the natural log of A at some time t versus time. And you get a straight line. See, I drew it straight. Okay? Your reaction is first order. So if I had some data, which we're going to do later on Excel, if I had some data and I graphed it, and I made a graph of the natural log of A at time t versus time, and I got a straight line, I'd be able to conclude that my reaction was first order. If I graphed the natural log of A versus time and did not get a straight line, then all I can conclude is that my reaction is not first order. Okay, so this is kind of helpful to us in determining graphically if a reaction is first order or is not first order. In just a little bit, we're going to learn, well, if I didn't get a straight line, how do I know if it's second order or is it zero order or whatnot? So that's where these your axes are going to change. Okay, what you're graphing is going to change, and that's going to lead you to a determination of what order the reaction is. So I'm sure right now you're like, I don't really see, the point of this, but we'll get there, I promise. Okay, so there is a practice problem. It's a little bit lengthy, but it's really not that hard. So we'll do it together. Let me erase this, and then I should have left that reaction up there. Okay, so I only have one equation. So here's my practice problem. Holy cow, it's long. The decomposition of some insecticide in water follows first order kinetics. Has a rate constant of 1.45 years to the negative first at 12 degrees Celsius. Some quantity of this insecticide is washed into a lake on June 1st, and that has a concentration of 5 times 10 to the negative 7th grams per cubic centimeter. Assume the temperature of the lake doesn't change, it's 12 degrees Celsius. And so A wants to know, what's the concentration of the insecticide on June 1st of the following year? Okay. So a whole year's gone by, right? That's your time. A whole year's gone by, 1 year. I know my rate constant, they just came right out and told me it's 1.45 years to the negative first. And they gave me the concentration of the insecticide when it first got put into the lake. And that's the initial concentration. So I know this. I know it. I must be looking for this. So here we go. What's the concentration a year later? So I'm going to take this guy to the other side. And now I'm just plugging numbers in and solving this, okay? So they told me what K was. Just watch your negative. Don't drop your negative. Negative 1.45 years to the negative first. Times my time, which was 1 year. Notice your units are going to cancel, right? Plus the natural log of the concentration of A at time 0, which was initial 5.0, times 10 to the negative 7th grams per cubic centimeter. Okay. Done. So cancel, and I go to solve this. The natural log of A at time t is negative 1.45 plus, I did not bring my calculator in here, so I don't know what that answer is. Here, let me see if my phone will do it. Let's see. 5.0 times 10 to the negative 7. Yeah, so that comes out to be negative 14 and some change. 508, blah, blah, blah. And then if I add those together, so I get the natural log of A at time t is equal to negative 15.96 and some change. And you might be saying, what in the world? But see, we haven't solved for concentration yet. This is the natural log of the concentration. So to get rid of natural log, you do E, right? I'm sure you've learned that somewhere in your math class. Which means I'm going to take E and raise it to the 15.96. or negative 15.96, and I get out a concentration of 1.2 times 10 to the negative 7th. Units are going to be the same. Just going to carry down. And so that's my concentration a year later, okay? Notice it's gone down, right? It has to go down. It only makes sense for it to be smaller, and this number is smaller than this. And so I have determined the concentration of that insecticide a whole year later, okay? So that is how that first part was done. And now we have should have left that. We have part B. So let's see, what does part B say? Part B says, how long will it take for the concentration of the insecticide to drop to 3 times 10 to the negative 7th? Okay, so in this case, I must be looking for time, right? How long will it take? So I want to rearrange this equation for t. I need to get rid of my negative k, so I'll just divide. So t is natural log of concentration at time t, natural log of initial over negative k. Plug in, I should be done. So let's see, k is the same. Natural log of concentration of A at some time would be the 3 minus the natural log of the initial concentration, which was that 5.0. When I do this, as long as I don't make a math mistake, my time here should come out to be positive. And I got 0.35 in my answers in years. Okay, so according to this, it'll take about a third of a year for my concentration to decrease from 5.0 times 10 to the negative 7th to 3.0 times 10 to the negative 7th. Okay, so basically the use of this formula is just an algebra discussion, but the bigger idea here, and this is a huge takeaway point, okay, the bigger idea is that if I take information from a reaction that is first order, then the graph of the natural log of concentration versus time will give me a straight line. Okay, and then I would be able to confirm that it's first order. Its slope is negative k, and its y-intercept is the natural log of A's concentration at time 0, which is initial. Okay, so I know there's still a lot of missing pieces here, like what's the point? What happens if it's second order, okay, and all that good stuff. So that's only the first page of this packet. I feel like this video has already gone on too long. So I am going to go ahead and stop this video and do a second video for the next page. This packet's going to be broken up into several videos because there are kind of a lot of different topics. But that was the background and first order. And so we will do second order, 0 order in an additional video.